mic to you. I actually do need this mic. So welcome to the afternoon keynote. It is my pleasure to introduce Dr. Kostas Alexis, full professor in the Department of Engineering Cybernetics at the Norwegian University of Science and Technology, and director of the Autonomous Robots Lab. So without further ado, here we go.
Thank you. Sorry. Thank you, everyone, for attending the talk, and thanks, everybody, for the invitation. Thanks for the organizers that invited me here and gave me the opportunity to give a talk about our work on resilient robotic autonomy, how we can build resiliently autonomous robotic systems, and how I will talk about this on the basis of the experiences of the DARPA Subterranean Challenge and our team participation there, Team CERBERUS, alongside, of course, new research that projects upon the experiences of the DARPA Subterranean Challenge. But to give a good insight about what I want to say, I would like to first introduce you into this type of environments and a world that is less simple, more dark, more challenging than the one we typically operate ourselves or that we typically deploy robotic systems. So in the results that you see here, which represents previous work of the team or results during Team CERBERUS alongside the results that came afterwards, you will all see robotic systems flying or legging together with our partners from ETH that will be exploring what I will call dark, degraded, communications denied, and perceptually challenged environments. Or in other words, challenging settings where we would like to be able to deploy robotic systems to explore, map, inspect, and characterize instead of having to set ourselves first. So just to give some example of what you see robots in underground mines. You just saw a robot in a nuclear power plant, a robot inside a ballast tank of a maritime vessel, and you'll also see results of drones flying in under canopy in forests alongside a host of other environments. But these are all examples, and what I want to discuss today is how we can build resilient robotic autonomy across such robotic configurations. So let me then go directly to the underground together with the results of my team, Team CERBERUS. But to first comprehend and understand the value of the work of the DARPA Subterranean Challenge, it's important to get an understanding of underground environments themselves. They are very diverse, and DARPA coded this into three settings, what they call tunnel, with underground mines being a prime example, urban, such as urban subways or natural infrastructure, or critical infrastructure such as nuclear power plants and so on and so forth, and cave networks, natural caves, such as lava tubes, karst caves, and so on and so forth. But beyond this characterization, within each subcategory, it's critical to understand that there is great diversity. You know, a karst cave has very little to share with a cave in a glacier formation, and we want robots to be able to go in all three types and across all variations of these three types. That was the goal of the DARPA challenge. And the latter thing to remember is that subterranean environments, although we don't really look at them very often, they represent the trifecta of resources, for gold, for lithium, and so on and so forth, possibility to explore biological worlds on Earth and in space, as well as host a set of activities such as transportation and so on and so forth. And if we want to go a little bit wild, we will say that the contribution of the DARPA challenge, not necessarily our team, but the challenge itself, is both for such activities here on Earth, but we know from the team, Kostas from NASA JPL, that they believe it's also applicable to other worlds on Mars, on Moon, and so on and so forth. But without delay, let me go directly into the DARPA challenge itself. It was organized on 3+1 stages of a competition, with the tunnel circuit, the urban circuit, and the cave circuit asking teams to participate in a challenge specified to the particular environment of interest, the tunnel like a mine, and so on and so forth. The teams that succeeded in every such stage progressed to the next stage and eventually to the final event, which was comprehensive. The final event itself combined the environments of the previous type of tests. So we first went to the NIOS underground mine in Pittsburgh, then went to the Satchel nuclear power plant in Washington State. We didn't go for the cave circuit because of the COVID-19 imposed restrictions. The teams that succeeded up to the second tunnel moved to the final stage. In the final event, DARPA went to the Kentucky mega caverns, a massive environment, according to what I read there, is able to host 60,000 people underground, and developed a mega area that hosted what was called the tunnel area, the urban area, and the natural cave environment. The tunnel looked like an underground mine. They built something that looked like a subway alongside other urban infrastructure underground for the urban segment, and they used the natural environment alongside some further facilities they built for a narrow part of a cave. and asked us to deploy robots from the beginning of a single point of entry from the DARPA gate, have the robots be commanded by a single operator only once the robots enter the stage without communications being available other than those that the robots themselves could facilitate. And to get a point, you should be able to detect an object of interest from known classes and localize within 5 meters of error, absolute error, against the DARPA frame. Your only chance to get an initial alignment with the DARPA frame was a gate in the beginning with fiducials such as April tags, and then it was all about your SLAM on board. So with that, let me then get you to the DARPA challenge together with my team CERBERUS. I'm Greek myself, so the name stands for Collaborative Walking and Flying Robotic Systems for Autonomous Exploration in Underground Settings. But the acronym CERBERUS comes from the mythology of ancient Greece, and it was supposed to be the three-headed dog that protected the underworld. And the idea came that we are using legged robots from our partners from ETH, flying robots by us and other partners of the consortium, and of course, humans. So this is the consortium of the team. I was back then when we started at University of Nevada, Reno, and I was the chance to be the team lead of this great team. Then I moved to NTNU. We have two labs from ETH, RSL, Professor Marco Hutter, and ASL, Professor Roland Zigvart. Berkeley with Professor Mark Muller. University of Oxford with Maurice Fallon, Flyability, a company, and Sierra Nevada Corporation. And I want to take a pause and say that whatever you're going to see, first is the result of a team. And I want to take, alongside thanking everybody in this team, I want to take special time to thank my own lab for their continuous efforts, and especially also my friends from ETH, both RSL and ASL, for their contributions, which you will evidently see in the videos that follow. So these are the robots we brought, not throughout the 3 years of the challenge, but just for the final event in September 2021 in Kentucky. And this gives you an understanding of the diversity of the developments in this project. And I will be using this diagram to discuss throughout the several modules of building and instilling resilient robotic autonomy throughout our robotic systems and how this projects to future research. So of course, we start with the backbone of resilience, which is the robotic systems themselves. And we start with a subset of the machines we brought in the competition, Animal C at the end, initially with Animal B, and a host of flying robots of two categories, larger and smaller, smaller with collision resilience, and the larger, of course, not. I will spend very little time for the robots, because most of you have seen most of these machines in a host of papers or in live demos. But I want to just indicate that we are using two types of legged robots. The first two having purely the role of exploration and detecting artifacts, objects of interest. The second, executing this role alongside walking and deploying communication breadcrumbs, essentially mesh nodes on the ground to facilitate the communication network on their own as they progress and explore the underground environment. Aerial robots as scouts to move fast, fly, and explore. Initially, we had the plan to ferry an aerial robot marsupially with Animal, but we did it after the competition due to the COVID restrictions that eliminated some of our integration time. And at the end, we also brought a rover, which we used with an optical fiber cable all the way up to the gate of DARPA at the beginning, and a high-gain antenna that helped us to facilitate communications underground. And of course, the ground systems have a lot of payload to carry a host of sensors. You see here Animal Explorer carrying 3 LiDARs, 7 RGB cameras, fixed ones, alongside an inspection payload that involves a rotating RGB camera with zoom and a thermal camera. And the flying robots naturally carry less sensors. And these are some instances of what will come next with further detail, with Animal walking in an area filled with smoke, our flying robots flying in confined environments, and on the right, a flying robot going down a level in order to explore another part of the nuclear power facility at Statue of Washington. And I want to take also here a second to credit the work from our partners from RSL, because the robot never fell in the final event for a single time. And I think that's the only legged robot that was deployed that didn't fall throughout the final stage of the competition. So credits to the machine itself and to the locomotion controller. But I want to now focus on what is special in terms of perception and autonomy on this challenge, and I will start with perception. So in these environments, GPS denied, of course, is a natural assumption you should take. The second is that we don't have good light, good illumination. But that's not only the real problem, because we could carry illumination ourselves. The problem is that the environment is not featureful. You know, if you are looking at a car's cave, it's just black most of the times with very little and weak texture often. If you look at a glacier cave, there is pretty much nothing to look at distinct features. We might have self-similar geometries, like a self-similar tunnel that degrades LiDAR naturally. And we might also have obscurants, such as dust and smoke, that degrade both LiDAR and vision, and typically render most of the localization solutions nowadays unable to perform. And this is not theoretical. These are images from the DARPA Subterranean Challenge finals that present each of these challenges that I mentioned at instances of the run of our team during the final stage. And early in 2018, when we started working on this challenge, when we literally submitted the proposal, we were also working on the solution SLAM-wise that will allow us to penetrate these conditions. And the idea was relatively simple at the day, was to cascade and fuse in a loosely coupled fashion a multimodal solution involving LiDAR, vision, long-wave infrared thermal vision, and of course, IMU. And the key is that so long, back in the day, we developed some heuristic functions, at least to start with, that allow us to detect which degrees of freedom for each estimate, let's say visual inertial, or thermal inertial, or LiDAR odometry and mapping, is degenerate at each time. We are able to use the best estimate for each of the degrees of freedom of the robot as the robot operates in the environment. So if it's self-similar geometry, then LiDAR is about to fail for this particular direction. If it's full of dust, then vision is also about to fail. If it's very dark and with low texture, vision is about to fail. So we had also then explicit functions to detect these degeneracies. In particular, we're using the eigenvalues of the underlying approximate Hessian on the LiDAR odometry and mapping problem. And for the visual inertial / thermal inertial solution, we thresholded the d-optimality metric over the covariance of the solution as the odometry estimate was updating itself. And this allowed us, as mentioned, to use from each modality, each solution, the best degree of freedom, let's say for X, Y, Z, and orientation, and then combine this estimate to update the odometry of the system and the map of the environment. And you see the principle on this simple video, which is back in 2019. We are navigating, we're flying inside the self-similar tunnel. And of course, the x-axis is degenerate for LiDAR. Vision, of course, has no particular issue in this environment. And this allows us for a robust estimate as we go. But that's probably not very fancy or very exciting at the moment. So the next one is a bit more interesting. If we want to fly through dust and smoke for some types of particles of obscurants, we can use long-wave infrared. And by solving an optimization problem in slightly window fashion and using a direct formulation of the error, we're able to go in the environments such as the one that you will see momentarily, where we are inside the mine. It has very weak thermal gradients, so therefore we are using the full resolution of the thermal image, unlike taking just the normal image as an 8-bit array. And we are essentially demonstrating that we can have approximately as good odometry as a LiDAR solution that we had developed a priori for ground truth. In this environment, despite, of course, being with lack of visual texture, we are using the thermal camera at this point, and despite that, the fact that in the beginning we had deployed some smoke. However, I want to say that as it comes in few slides later, you will see a much more smoke-filled environment. And although in the final run of the competition, we solely relied on onboard SLAM on the systems, we had developed, together with our partners, a solution for multi-robot mapping that assumed that each robot had odometry update on its own, as mentioned, and then communicated to the ground station constraints from LiDAR and from vision to build a collective map that aligned all the robots, optimized the solution, and merged the maps of all the robots inside the underground environment. And this is, for example, a test that was done before with 4 robots exploring an underground mine called Hagerbach in Switzerland. And in terms of perception, just mapping alone is not sufficient to get a score in this competition. So it was also essential to detect objects of interest, find the correct class, and report the location. And the objects were coming from visual traces, visual signal, thermal signal, such as a vent that was essentially warmer, gas, CO2, and also we had to develop active devices such as cell phones and report the location. And to the latter, we also exploited multi-view consensus in some Bayesian form to robustify the detection and allow limited cognitive load for our operator. So with this brief walkthrough, the perception part of Team CERBERUS, let me go into autonomy. So if we have a good map, the next big challenge of the competition was that we had to deploy these robots to explore several kilometers of underground networks. At instances, they were particularly narrow. They had told us less than 1 square meter, and they actually made true of themselves. They had very narrow settings in the DARPA finals. And we had to explore efficiently, because we had limited time, to find the distributed objects of interest that gave us score. So to that end, much like our SLAM solution, we invested from the beginning into a unified path planning algorithm that enabled autonomous exploration and visual search by means of bifurcating in two modes of a local search and global graph. In local search, the robot allowed to incorporate multiple utility functions for exploration, finding, pointing the cameras where they have to be, because, of course, LiDAR give us volumetric understanding, but cameras give us the points. And then, at the same time, also account for collision avoidance, traversability aspects, positive slope maximum for animal, negative slope to be negotiated so that the robot doesn't fall on a cliff, and so on and so forth. And at the global level, we stored frontiers to continue exploration if the current area was already depleted, communication nodes where the robot could backtrack to come back to communications because there was no continuous communication throughout the run, areas that the robot could come back to completely home if it has finished the mission, and of course, the ability by the human to send some waypoint if this is necessary. And what you see here is results from the DARPA finals, with the robot negotiating a host of different cases, planning over rails, planning over positive slopes, planning over stairs, going to frontiers to continue the exploration space, retracting back to areas of good communications, and so on and so forth. And this was the main planner commanding both walking and flying systems. And for walking in particular, because the volumetric presentation we were using was not sufficient for traversability, this path was further refined by another planner, by our partners from RSL, that explicitly accounted for more high-resolution representation of traversability for this robot. So these paths were refined just to make sure that the robot is more safe, and you see the result when it had to negotiate rails of a railroad path. And it is important to say that both during the challenge and after the challenge, we keep building along this technology and deploying in underground mines, in the main video in the bottom right, as well as other confined facilities such as ballast tanks and so on and so forth, pretty much with uniform success for diverse robotic systems, all of course being able to run on board in real time and so on and so forth. And the pink paths is what you see there is commanded for autonomous exploration. And this on the left, on the big video, you see roughly 37 minutes of continuous autonomy without any human interacting with a robot at any given time. All right, so this gives us an understanding of the core autonomy blocks of Cerberus. In this talk, I would like to present those, but also then present the results and project to the future, because that's already a 2-year-old challenge. The last thing we had to deal with which we dealt in a very bad way, I must say, as a team, compared to the other competitors, was comms. But eventually, we relied on an off-the-shelf solution from Radiant, and we developed some breadcrumbs that allowed animal to walk, and as it was walking, it would just duck to deploy a communications breadcrumb, alongside the flying robots connecting to the mesh network, and the rover that you see equipped itself with a high-gain antenna and an optical fiber being dragged all the way from the ground station. So this is not necessarily the most elegant solution, but in fact, we invested more in autonomy, and I will show later in the results that the instance that the robots are not running in autonomous mode are very limited throughout the 60 minutes run of this final stage event. Now, alongside the technology, the next key thing for such a robotic system is to be field ready. And of course, in academia, we are not supposed necessarily to make systems be field ready. But what I mostly mean as being field ready is that although we invested on systems that were far less mature compared to, for example, let's say rovers or trucks, it is key to go into the field to identify core limitations in the algorithms that will then allow to be improved in order to facilitate resilience. So we had this pretty nice testing regime, visiting places all around the world, from Europe to the US, and so on and so forth, across both sides that the team was at any given time. And we tested multiple times to the level that before the competition, we had a bi-weekly run for testing the systems before eventually going to the final competition and deploying there with success. So now let me just walk you in a relatively brief fashion of competing in the 3 stages of the competition: the tunnel circuit, the urban circuit, and the final event. In the tunnel circuit, we went with very limited success, I must say. All the way to the last, we had 4 runs. All the way to the last 4th run, we were pretty sure we might be among those eliminated. We were among one of the only 2 teams in the competition that invested from the beginning in legs and flying systems, and we didn't have the best of success, alongside the second team that invested in this technology, which was the team led by UPenn. But with a last night insane activity that several people took the rover and deployed all the sensors and all the stack for localization and mapping and getting artifacts, and a great operator, Marco Transato, who drove the system with a remote control joystick, we managed to get sufficient points to go up to the next level. And maybe this is not a testament to our systems as the technology was being developed, but it's a testament also to the quality of the team, which I think is the most important resource in such a competition. And at this point, Carnegie Mellon, of course, with Team Explorer, showed who is boss with 25 points when we only scored 5. In the next stage of the competition, in the urban circuit, we had already reliable systems with technical challenges. We didn't manage to walk successfully over stairs, for example, or actually go down over stairs. We managed to fly down the stairs, but without being able, after flying, getting a point there. But we were good enough. We also progressed to the next level. And we had actually the most important thing for us, which was reliability. So we were deploying the systems, we were exploring as much as we expected, and we were able to get the points if we are passing through an object of interest, which was the first point that we showed that we have the premise to execute the mission exactly as we wanted. That was the urban circuit in a nuclear power plant in south of Washington. In the final stage, we went, and I had a bet with one of my close colleagues, Marco Hutter, and we said, who is going to get the money if we get at least third? And I told him, if we get at least third, we can get as much money as you want at ETH at this point, because third for me is enough, and then $2 million is something we can get always from a grant. I didn't execute this promise exactly as said, because I had to keep some of the funding, but it was a promise I actually meant. And we showed from the first 1 or 2 runs that we had reliability of systems, and we understood also, I think successfully, that it was also pretty important to identify the most applicable methodology of deployment. And we identified that DARPA had invested in very narrow environments where it was applicable to walk with relatively modest speeds. And we executed what we called breadth-first exploration, which means that the operator was just commanding the robots to go up to a certain area to explore by defining some bounding boxes. And only when this was executed successfully, progress to a second level of exploration, like a tree, and so on and so forth, right? So making sure we get the points of the areas that we explore, compared to just exploring aggressively without getting all the points of objects that might be applicable. We changed systems. We had the Animal Sea at this point, alongside another set of robotics systems available. And the 60 minutes of run that eventually DARPA allowed every team to run in the environment is something that you see here, sped up too fast. And you will see us deploying a total of 5 robots, exploring the different parts of the tunnel segment, the urban segment, the cave segment of the environment, with each of them having diverse properties, necessitating either to go through tough terrain, large areas, narrow areas, very vast areas towards the end, which is an actual room of the Kentucky mega caverns, and so on and so forth. Although the majority of it is actually pretty narrow and confined environments, which was, I will say, ideal for the type of robotic systems we had invested. And to give you a better understanding, instead of this video from the cameras that DARPA had deployed in the competition, this video allows you to see the robots exploring and planning the paths as they were coming from the planner on the localized solution by the onboard SLAM running on every system. And you see also the points being detected. We were using YOLO, just for the sake of finding visual detections, a CO2 sensor, as mentioned, and Bluetooth to detect some cell phones. And this is a long video, so I'm not going to play it all. But I also want to highlight that in this final run, the rover did not score any points, simply because there was no need. We only deployed it a few meters in front to provide some better communications for the overall robotic system of systems. This is the final map. It is roughly 1.25 kilometers of exploration, if I remember correctly. And these are the points we score. All points observed were successfully localized within the 5 meters of error, and no point was possible to be acquired in the areas we explored. In other words, every object that was in our passage, we successfully detected and scored the point. And what you see here, if you see orange, this means that the machines are working autonomously, and if you see blue, it means that the operator is intervening and executing some high-level commands, most likely to just give new bounding boxes on the robotic system. And the robot at the end, which is just not doing anything on the lower plot, there was a door that was opening and closing, and we have roughly 30 minutes or more that the robot is continuously trying to walk, coming back, trying to walk, coming back, and so on and so forth, simply because we didn't have a specific way to handle this, which was a limitation of the solution, but luckily did not cause a major problem. Still, quite some work to be done. And this is the score. Our team, 23 points. 23 points out of 40. Also, CSIRO, our competitors and friends from Australia, also scored 23 points, but reported the last point with delay compared to us, so the tiebreaker was in our favor. But I want to credit their fantastic work, alongside competitors from CU Boulder, Carnegie Mellon, NASA JPL, MIT, and CTU Cross, and University of Laval, and other partners. It landed us the winner of the competition, $2 million as prize, and also recognition from the US Senate. And most importantly, beyond the prize award, I think what it landed was also a great partnership throughout 3 years that to a certain extent also continues in some form or fashion now in new projects and new activities. Good friends, and I think I want to credit the guy that you see up there trying to open a beer because he was the single human taking all the stress, running the robots during the 60 minutes of the final run, alongside, of course, all the other team that you see in the photos being drunk after winning the competition. And there are many publications alongside this line of work, but the 3 ones that you could check for an overarching view is a science robotics paper and 2 papers on field robotics summarizing our run from the tunnel circuit, urban circuit, to the final event. Now, I promised from the beginning that this is not going to be a talk for SAPTI alone, because I consider that 2 years later, we should have valuable lessons about what to do next, and we should have executed some of that in new research. So we want to facilitate autonomy that has the capacity to go anywhere, with diverse robotic systems depending on the environment of interest. And my main claim is that to do this, we need to facilitate resilience, which I code as autonomy methods or systems that are robust in terms of performance, present redundancy in order not to fail, and have resourcefulness to combine different ways of methods, systems, sensors, processing solutions, control algorithms, navigation methods, et cetera, to make sure that there is always one way for the robot to continue its mission without failing. And I will start with 8 lessons learned from the competition, and I will focus on a subset of them to describe new research that goes beyond what we showed back then in the DARPA challenge from our side in my lab. The first, of course, is that you go as far away as your robots can go, right? So the backbone of reliability and resilience is the robot itself. The second is that we need multimodal SLAM to go through perceptual degradation, but we can do much more and much better compared to what we did back then. The third is that we know from all the other teams, or at least a subset of the teams, that it was SLAM that stopped their ability to explore further in the environment. And because I don't think we can always say that we can guarantee SLAM is always working 100% or reliably, we need a way to keep navigating safely, even in the drift of localization or map failure. I want to highlight that we invested in a centralized robotic solution, but the lesson learned is that actually it was the ability of each robot to execute its own mission that gave us the success. And I think, of course, the correct way is to go decentralized and self-sufficient robotic systems. On flying robots, I believe that the investment we should do is robustness in uncertainty versus just being amazed by how fast they can fly, which is true. But I think the key question for autonomy is how fast they can fly when situations are unknown and difficult. We maybe should invest on active perception. There is a window here, not there. So that's fine, yes. We should invest on active perception, and hopefully I can change my slide. I can, so I can see on the screen. And I will go then each by some of those to describe some of the details of new research. So first, let me go into sensor-degraded environments. What I would like to say is that when we started the competition, we thought from the beginning to invest on radar. But for a set of reasons, and I think largely because of the lack of experience of the team at the day with radar, we didn't actually invest. But later, and up to very recently, we have been working on radar fusion together with LiDAR. And in fact, I'm going to highlight that a better way compared to the loosely coupled approach we did back then is a tightly fused approach that does not assume that there is a human engineer who has tuned every function of detecting degeneracy for any sensor. So in this factor graph that you see, radar is giving us velocity updates, exploiting Doppler velocity updates from the sensor. And LiDAR features, plane line features, are directly into the factor graph. And we're optimizing all together, which means that if a certain modality is degenerate along an axis, it is presented in the data, but it is not requiring any of us to write a heuristic function to detect it. Instead, the optimization over the factor graph over a sliding window will demonstrate which degrees of freedom are more accurate than others. These are the error terms that represent the 4 factors that we are using: IMU factor, radar, and the 2 types of LiDAR factors that I mentioned. And these are some results in a very interesting bicycle tunnel in Norway, where for 3 kilometers, it's narrow, it's self-similar perfectly, and it's for bicycles to just drive around. And of course, as you can see, LiDAR is bound to fail in this environment and quickly drift. Radar performs robustly, but of course, it's a less accurate sensor, at least in our experience, compared to LiDAR when this works well. But LiDAR still constrains the remaining degrees of freedom. Therefore, the collective solution, despite the perfect self-similarity of the point cloud, as you can see on the rightmost plots, the collective solution is a very accurate map of this bicycle tunnel. But perhaps a bit more fancy is this result, where the drone will take off in a completely smoke-filled corridor of a building and will navigate. What is interesting to see, you're all familiar with Arvis plots, the grid there is 1 meter. So this means that the LiDAR can only see up to roughly 2.5 to 3 meters ahead out of how degraded the environment is, where we tested both first and second return of the most recent OS0 Rev7 LiDAR from Oster. And it's the fusion of the two modalities that allows us to get this fairly accurate representation of the map. Don't be confused by the colors. They are colorized by intensity, because we're testing how the intensity values of LiDAR point cloud show themselves. And you will see when the robot actually comes back to the takeoff location that the corridor scale is correctly estimated. And of course, you can compare it with the original, with the map in the smoke-free area that LiDAR, of course, is accurate. The next key takeaway that I mentioned was survival navigation when SLAM is bound to break. And this not to replace the previous work or the focus on multimodal SLAM for sensor-degraded conditions, but this is to interleave a functionality that even if our SLAM fails for 1 minute, for 2 minutes, before we do maybe some loop closure or something like that, we can still navigate with safety. So the traditional paradigm is that we do SLAM, we develop a map, we freeze it, we trust it for collision-free planning, and then we plan a path that's collision-free on this map, and then a controller blindly executes it. Instead, we have invested on a policy that uses the immediate depth, a partial state estimate that does not incorporate the position to allow this position to drift slowly during mission, and the uncertainty over the partial state that goes up to linear velocities and attitude, to drive a robot, to fly a robot, in order to navigate in an environment that doesn't have a map, does not have full position estimate in a safe manner. And it represents this work on this neural net that you see, which relies on a collision prediction network that is fed with a depth image, the partial state, which is linear velocities and attitude, and angular velocities, alongside the covariance over this partial state, and a goal vector that might be approximate to the destination, as currently our SLAM is assumed to have fallen. And we will be focusing on embedding this work, both aleatoric and epistemic uncertainty, over the network that you see here. So for aleatoric uncertainty, we focus on the covariance over the partial state that we sample through the uncertainty transform, and we iterate and we infer over all sigma points from the uncertainty transform. And epistemic uncertainty relates primarily to the errors in the depth image of an RGBD sensor, let's say, in this particular experiment that you will see. And we train a deep ensemble instead of a single neural network in order to account and offer robustness against such issues. And the result that you will see is a robot that does not know the map, does not build the map, does not know the position. It only knows that it has to move forward roughly in this corridor and avoid the obstacles that it sees in front of it. And again, this essentially is to replace a traditional position controller that would just blindly execute a collision-free path sampled and planned over an otherwise frozen map that may contain errors. Now, if we have this capability, we might as well extend it to go back 30 years ago into ideas of active perception and embed into these systems the ability to look at areas of interest while it's otherwise navigating. So it could look towards that areas that are visually salient, or it could look towards areas that is an important object of interest, either bottom-up or top-down motivations. And we train another network, a parallel to the other one, which we call an information prediction network, and scores each motion primitive with respect to how informative it might be in the future. So this allows the robot to navigate and implicitly sample information that might be beneficial for the mission overall. In the result you see here also, the odometry truly has drifted significantly. So we show a map based on reconstructing it after the mission, but during the mission, actually the onboard odometry has truly drifted. And the robot will be flying, and when you see this red backpack, just to have a clear example for the sake of the video, it will just pointing itself a little bit to gather some more frames while it's continuing to its navigation path. All right, but of course, I think you could have a good criticism in this line of works, which is like, well, how can you be sure that you can train in simulation, as we did in this work, and be safe in practice? And despite the fact that we focus on uncertainty, aleatoric and epistemic, the fact is that the depth image we are using might contain a host of errors. So in the last period, we have invested with my team on modularizing this autonomy pipeline by first training an encoding step that reduced the high-dimensional image data to a very low-dimensional space, let's say, for example, 128 variables only, which is roughly 1,000 byte compression. And focusing on first verifying this latent space in its ability to reconstruct objects, even if they're very thin or generally hard to perceive, such as reflective, before we feed it to the network to then train the same otherwise previously end-to-end policy, now not end-to-end anymore, that predicts which path is safe or not in the environment. And to that end, we have specifically made sure that this encoder focuses on objects that are hard to perceive, let's say, for example, thin, or a good example might be the thin branches of a forest, let's say, a dense forest, not a forest that's sparse where we can just fly fast by avoiding only the tree trunks, but flying through branches and other small constrained and hard to perceive passages. And next, we train the remaining policy, finally, in an end-to-end manner with respect to collision prediction. And this is the result that you see here, where the robot now relies on encoding this latent space first, and then exploiting this compressed latent space to train the remaining of the collision prediction network in an end-to-end fashion. The result is pretty much analogous to the previous, with the difference that it has better capacity to deal with hard-to-perceive, thin, or reflective objects, such as those that you see in this video here. And very recently, the same PhD candidate that developed this work has extended to RL by first also revising the encoding step, because it's not compression of the image that we need, it's compressed latent space for collision. And in fact, predicting collision, if you study this a little bit, you understand it's a simpler problem compared to reconstructing the image. Because if there are two branches with 10 centimeters difference apart, we actually don't need to know both of them. We just need to know that we cannot pass through this area. Through some technique that is published, we developed what we call the deep collision encoder, and we're able to have a very compressed latent space, only of 64 variables, which is roughly 4,800 times compression, and then train with asynchronous PPO and RL agent to fly in a collision-free manner, extending the work that I mentioned before. And the result is essentially the same, with the difference that now we have much more naturally emerging behaviors. So here we constrain the robot not to fly up to avoid all obstacles by flying above everything. But if we allow it, of course, naturally, the robot, this is what it's doing, right? It's just flying above everything, because then this represents the least effort for the machine to fly safely and avoid collision. Now, I want to say some final thoughts as I conclude my talk and make sure that we have quite some time for Q&A. My basic final thoughts is that I think what we need is to go away from each of us developing only the individual module. This has been fantastic work from the community over the last decades, that we have amazing work in SLAM, in path planning, in learning, and so on and so forth. But I think we also need a holistic view on how we facilitate autonomy, and I would like to call this the science of resilient autonomy, calling for interdisciplinary work within the field of robotics about developing the methods that allow the robot to present resourcefulness despite problems in any of the functionality, which means that, for example, some sort of new level of control should fly the robot or walk or drive the robot safely, even if its localization has persistently failed for a while. And I think that's a natural paradigm if we think, for example, how we navigate. And I also think that this is to be combined both with fundamental research and, of course, developing systems that is reliable and testing systems in the field to verify and prove reliability alongside finding what to do to improve it. And before I close, I want to highlight that a lot of the work has been open sourced, both by ourselves as well as our partners, primarily the two repositories there, Lego Robotics and ETH ASL. From our side, the Oracle Planner that I mentioned before, the Exploration Path Planner, the Aerial Gym Simulator for training RL policies, for example, the Motion Primitives Exploration Path Planner, the controllers for all the robots, and so on and so forth, are all open source and available to the community to use, test, and develop further. And with that, I want to take 1 second to say that we are hiring along all fronts that I mentioned before, trying to find 10 people as PhDs and postdocs funded by the Horizon Europe program. And I want to thank my team, first of all, and I want to thank all of you for attending this talk and giving me the opportunity to present our work, for which we are very proud. And we look forward to continue further building resilient systems that allow machines to be ubiquitous, both in the naive environments, but also in the very challenging and very demanding settings. Thank you.
All right, so thanks very much. I think I saw somebody walking over to get where the microphones. So there should be microphones on either side.
Yeah, I was told that if there are questions, there are some microphones, and people should queue on the microphones. I don't see them from here because it's very bright.
Yeah, so I assume the volunteers can wave to people with the microphones. So.
But I can also just probably hear people if it's not possible.
So.
Yes.
Okay, so I have a question while we're waiting. How do you incentivize team-based, collective, interdisciplinary work in such a solo environment? So academia, by its very nature, is solo. And do you have any recommendations on how we would do that? So your team has been incredibly successful in doing so, but...
I think the best avenue for that is having a motivating challenge. And I think, I must say, this is the best service DARPA did to us. They didn't offer only the technical challenge, they offered the story, the vision, right? And I think this is what we need to build ourselves also, not only expect the agency or any other agency to do so, but this is something we need to build on our own and develop, identify hard challenges in the future and call teams to collaborate to try to address them. And maybe some people might want to solve them on their own, right? But probably collaboration is the best avenue.
Thanks very much. I think we have some people lined up for questions over here, so we'll start on this side.
Hello. Yeah. Thank you very much for the talk. I mean, I really enjoyed the effort, and seeing this collaborative effort got to the point that it was actually productive, both for the science side and for the technology development. I think it was a very nice achievement to show to all the people who are in the conference. I really appreciated that. I just have a quick question about single robot damage recovery strategy. So this is something that when you were mentioning about a single robot resilience autonomy, I think one of the major factors is that what if that robot gets damaged throughout the mission in some way? When you're working with multi-agent system, there are existing solutions for that, so that other robots, taking care of the task. But given the restricted environments that you have and a specific task for each robot, so each robot must be resilient somehow to some damages that is happening to the robot. Any thoughts on that?
Yeah. First of all, I totally agree that if it's possible, we should exploit multiple robots for better resilience. But for example, in a narrow corridor, if we just collapse on this corridor, we are most likely to just also block the way, right, for any other robot that might want to continue in this direction. So we did some work in this direction, for example, be able to stand up again and so on and so forth. But the best example, I must say, come from a competitor, CTU Crash, which not only had the ability to just recover software-wise, but they also stored the map right before a crash. They reloaded this map, and they were able to localize again on the previous so far aggregated map to continue the exploration should the robot be software-wise and mechanically able to come up again in life and continue the mission. So I think it is essential, as you say, to invest both on the hardware aspect of robot reliability, but also the software aspect that will allow to continue the autonomous mission. I don't think we did the best work on that front, and I don't want to claim things that we didn't do. But there are avenues like this, right? Storing your map correctly, finding on the map when the error happened, bringing this back to life, continuing the mission from at this point, and so on and so forth. So those will be some of the approaches. The second approach also is, of course, to invest on systems that have different ways of navigating. So for example, on the tunnel circuit, you saw at some point we flew above a collapsed animal because animal was blocking the way, so our only chance was to fly over it and continue the exploration mission inside the tunnel.
Thanks.
All right, thank you. And I think there's a question.
Okay, Kostas, thank you very much for the nice presentation and showing the impressive results. I have a question, given that you worked with a large number of different robots, different sensors. So how much of the components have been shared among the robots, and how much are individual to the robots, and how did you realize these kind of not reproducing all the components on all systems, but to actually make them interoperable?
Yeah, so I think for that we're very lucky to have good collaboration within the consortium. And in fact, if I was to give an approximate but pretty accurate answer to your question, will be that everything that relates to control is at the level of the robot. Everything that relates to maybe some refinement of the path specific to the dynamics or some constraints of the robot is specific to the robot handled by the team that develops this robot. But SLAM, exploration path planning, coverage path planning, artifact detection, localization of objects, communications, all these aspects were exactly the same, identical, across all robotic systems. The only difference, for example, in SLAM is that the same SLAM solution had an extra input for legodometry, fed into the otherwise fusion as a graph at the end. In the planner, the only difference is that for the legacy systems, we also accounted for traversability on the ground. But it was the same software, right, with just a flag switch. So we made sure that we invest from the beginning in a unified approach. Now, in principle, one could say that this might not exploit the best capacity of every machine. But I think it's the good initial approach, and then afterwards people can invest on specialization.
Okay, thank you very much.
Thank you.
Yes, thank you. Very wonderful talk. I wanted to ask a question a bit more on the underlying philosophy when it came to your system design and actually implementing that. At any point, did you realize if your approach needed to go back and try again, or to rather take in the resilience, like you mentioned in the previous question, of adapting the strengths of one system over the other and compensating for that? I guess my question was, what was your overall philosophy? How did that change throughout the whole challenge?
Yes, so I will give you my personal view on this, or the view of our team, which does not necessarily mean that's the only view, because there are other teams that did also very well and they had a different philosophy. So I believe for me, when I see a challenge of that nature, and I think we share this vision in our team, the question is not how to win the challenge alone, because I mean, we are not in our positions just to win challenge. The question was how to progress technology of interest to us, to which we know we can develop further, while also bringing this technology to a level that can win a competition of that nature. Because we believe from the beginning that although, for example, walking and flying is not the most easy solution for this environment, and probably taking a big rover or a truck system is a more, let's say, high TRL solution at the moment, it is the one we believed is better in the long run. So despite the fact that we failed miserably, although managing to pass over the first stage, but with a very low score in the tunnel circuit, we didn't go back to change fundamentally our solution. We added some resilience, bringing the rover also with sensors and so on and so forth. We had a lot of discussion in the team, and naturally with 50+ people involved, we had different thoughts throughout the competition. But we persisted along the main directions of the solution, as we promised in the beginning. And I think that's a valid approach to take in these competitions, because the question is not how to win it, right? The question is, what is the technology that could win the competition or could do best? And this is the technology we could contribute, and this is the one that we push further, both in terms of systems, SLAM methodology, path planning methodology, and so on and so forth. And there are other approaches, of course, and I understand they're also pretty much valuable, but this is the one we took, right? So we didn't really change, although we had a lot of times that we thought, should we do a significant change? And after a lot of consideration, we identified that investing on the prime approach we promised in the beginning is the one that makes sense for our team most. And I think, to a certain extent, at the end of the competition, from all 3 runs, this is the key takeaway that we could take, that fundamentally the approach of Cerberus was correct in terms of systems. Everybody also afterwards focused on multimodal SLAM solutions, and maybe people also had better communication solutions, better systems in some sense, depending on the condition and so on and so forth. For example, CSIRO had the best, most accurate SLAM solution in the competition, but the fundamental approach, I believe, was correct.
Thank you.
Here in the hat.
Hi, Professor Alexis. Thank you for the wonderful presentation, and congratulations on winning the first place in the DAPRA Subterranean Challenge. It's great. So personally, I'm working on UAV side. So as a UAV engineer, and I think the problem for me is when I was looking at your video showing the UAV was navigating in an indoor environment. Something came into my mind is just that there's a normal UAV or quadrotors. The power budget on it can only support the UAV to be airborne for half an hour to an hour, and also not to mention you have to use the same power budget to power a 3D LiDAR, onboard computer, or cameras, a lot of stuff. I think you might have involved for the UAV to dock itself to the power station, and then start charging itself, and then restart the mission again. But on the other hand, would it be possible so you have auxiliary robots that can help the UAVs or even help the quadruped to exchange the batteries as well while in the mission, so the mission will not get interrupted by the power budget? how would you, think of like which solution would you be more preferred to do? That's my question.
Yes, thank you. So two answers to that. First of all, from the beginning, we had promised, and you may saw that on the rendering video, that the small quadrupeds, sorry, the quadrupeds are carrying onboard small quadrotors that are to be deployed marsupially, as we call it, right? So this means that we use this time-constrained resource where necessary. The obvious case that you are in a big cave and you take off to have a high vantage point, right? Now, this was a solution for the challenge. We completed the solution with our partners after the challenge due to COVID restrictions. But I must say, working in UAVs also for many years now, I'm a little bit, to put it very bluntly, I think we should move beyond quadrotors, right? Or beyond just copying a manned design and just miniaturizing it. I mean, from my PhD times, I had this page that the design of the quadrotor has its roots in the beginning of the 20th century. And we are now 2023, and we keep just doing the same, but better. And I have a project that I'm starting now in November, where the idea is computational design of robotic systems specialized on their mission and environment. So instead of focusing only on generalizing robots to all environments while keeping the same design more or less, like such as the quadrotor, trying to find, by means of the success ratio in navigation, the most applicable design for different types of environments. In other words, if we have a robot that is to do outdoors inspection, by just observing some areas from high vantage points without any obstacle around, and we have the same design but smaller, trying to fly inside a confined cave, I think fundamentally we're not doing the best job. And I think this is a good time now to change paradigm. I understand that in terms of results, the best avenue is to do better on the same platform, but in terms of results in the future, maybe it's a good time to make a change.
Yeah, thank you for a very insightful answer. Thank you so much.
Thanks, and we'll come over to this person.
Yeah, thank you for your impressive talk. Your whole system is almost autonomous. So I'm really curious about what is the role of the human supervisor in the competition, and also what is his work?
Right, very, very good question. I didn't spend the time to explain this. So let me just recap some properties of the DARPA competition. Once a robot enters the stage, the only person that is able to is allowed to communicate with it is a single human, which means from the beginning that if you have multiple robots, even if there was communication between all of them and to the ground station, you should reduce the applicable cognitive load, number one. Number two, in an underground environment, if you are in an intersection and you're turning right, and there is walls, rock wall here and rock wall to the right, your comms are immediately stopping at this point. If you're using Wi-Fi or anything like this, you don't have communications moving forward. I mean, you can use some sort of special communication for underground environments, but this means huge antennas, very long, because it's just how the spectrum works. So essentially, even if you deploy some communication breadcrumbs, you should assume that a lot of the mission is purely communications denied. And I think this already drives that the correct solution, not necessarily for the competition that it was only 1.5 kilometers or so, but for a true mission of interest, let's say to save somebody in an underground mine, just to give a parenthesis, an actual underground mine called El Tiente is 2.4 thousand kilometers in length, plus, according to which source you read, right? We're talking for vast environments. So if we don't have comms working, we need to have true autonomy. Under these two assumptions, the applicable design we got was that the human is there to send the robots in, of course, makes the decision which is the resource we are putting in at the moment. We give the human a set of possible robotic systems with different capabilities. He or she is the person to decide what is to enter. The second, the operator is to decide if there are comms, the general bounding box over which each robot or a team of robots should explore at this point. When a robot comes back to communication point and eventually streams back a part of the map to inform the operator about what is going on, at this point the operator can provide new insights about the areas to be explored. We coded this supervised autonomy in the absence of another term, but essentially it's an operator that interacts with a machine that has a high level of abstraction. And I think that's the applicable way. We did have the functionality to walk at a certain point, take off from here, restart your particular node, and all the low-level functionality you expect us to have as engineers. But this was not to be used in the normal conditions.
Yeah, but I have read your paper before. It's about subterranean charge. You have mission-level autonomy, so isn't it enough or not? Because I know that one of the tasks is about how to deploy the node autonomously. And the other thing is how to recover to the courage of communication. So I'm really curious about that.
So the deployment of the node was by the human. So
Yeah.
the robot was walking, and the human was reasoning at the end of in the final run, right, what we actually did. Because we investigated several ideas, but what we actually did. In the final run, when the human was reasoning that this area is necessary to drop a node because the robot is about to turn right on a rock wall, for example, then the human was just deploying this node there. And the idea was that the operator makes the decision while the robot is in comms. Now, the moment we also explored the graph, we annotated every vertex of the graph of exploration with it having or not having good communication signal. And then the robot, when it was out of communications, after an allotted amount of time, we gave to this robot 10 minutes in the final run to go to the next area of exploration. After the end of this allotted time, it will have to come back into one of the graph nodes that had good comms. And then inform the operator, and the operator was giving another high-level command, now take this area.
Yeah, thank you.
Thank you.
We'll take one last question from here.
So my question is about inspiration from biological systems. So at one level, you have the quadruped, which is to some level biologically inspired, and that's more obvious biological inspiration. But when it comes to resilient autonomy of a team, I feel like biological systems are very good at adapting to changing scenarios and what you talked about, sensor degradation, etc. Were there any ideas that helped you in this process, and if not, do you see any opportunities for biological inspiration?
Yeah. Well, I think that's a question that is captivating, and I got a book at some point called Subterranean Habitats, and explains how beings live in true subterranean worlds, right? And some of them troglobiotes and so on and so forth. And I think, in principle, the inspiration we can get, but translate to what we can achieve properly engineering-wise, is both sensorially, that essentially you cannot rely on visible light spectrum, for example, and the most difficult one that I think we haven't managed to integrate by no means is how to be energetically efficient. I think a true criticism is how this team can operate in an actually sized underground world, right? Mammoth Caves, for example, in Kentucky are more than 640 kilometers over span. So I think we need to see how we can make systems energetically efficient, not by mimicking what is there biologically, but by getting the inspiration that this is something we're not doing as well as necessary for this type of environments. That's the first clue. The second clue that we're getting is sensorially, that I don't think we can invest on visible light cameras, for example, in these environments, and so on and so forth, unless we continuously want to carry good illumination and hope they're good. There's good texture also, number two. And number three, I think the other key aspect is to identify, especially as we say, outside of the ground platforms, how to fly more efficiently in these environments. Because if we are mostly hovering and we are not exploiting some sort of more dynamic flight, by design, by airframe design, then we are necessarily energetically inefficient. But of course, this is my thoughts. It's very open, so I think it's very good to get inspiration, but I don't have the answer to this last captivating but very difficult question.
Thank you.
All right, thanks everybody for the questions. Thanks to Dr. Alexis
Thank you.
for the wonderful talk.
Thanks a lot.